This is part 2 of a lecture on section 5.5 in Math 311, a course in linear algebra at Western Illinois University. So, I want to do one more example of how we can use linear algebra to determine whether a binary quadratic form is positive definite or negative definite or or indefinite. So here we have 2x squared plus 6xy plus 5y squared. So the matrix corresponding to this will be 2, 3, 3, 2. Okay, once again, we have a 3 here because that's 6 divided by 2 is 3. Okay, finding the eigenvalues, we have 2 minus lambda, 3, 3, 2 minus lambda. That will be 2 minus lambda squared minus 9, which will be lambda squared minus 4 lambda plus 4 minus 9. Okay, if I didn't do something wrong, let me see. Oh, I see. Yes, I did do something wrong. This should be a 5. Okay. All right, so let's fix this. Okay, my bad. All right, so this will be 2 minus lambda, 5 minus lambda minus 9. So this will be lambda squared minus 7 lambda plus 10 minus 9, or lambda squared minus 7 lambda plus 1. Okay. Sorry. Math professors make all kinds of mistakes as well. You know, we were so worried about the 3, I forgot about the 5 here. Okay. Well, hopefully no harm, no foul. And now here, this is not going to factor very nicely at all, so we have to use the quadratic formula. Where A is 1, B is negative 7, and C is 1. So this tells us that lambda is going to be 7 plus or minus the square root of 49 minus 4 times 1 times 1 over 2 times 1, which reduces to 7 plus or minus the square root of 45 over 2. Now we could simplify this a little bit, but we're not going to for our purposes. We can see that lambda 1, if we take lambda 1 to be the smaller eigenvalue, and lambda 2 to be the bigger eigenvalue, we can see that these are both going to be positive, because 7 is bigger than square root of 45, because the square root of 49 is bigger than the square root of 45. So these are both positive. So this is going to be a positive. This is going to be a positive, definite binary quadratic form. And in fact, what we can see that what we're saying is 2x squared plus 6xy plus 5y squared is going to be bounded by these two eigenvalues. When we are subject to the constraint that x squared plus y squared equals 1. Okay. To get equality, you need to find the eigenvalue, the eigenvectors corresponding to these, and trust me, these are going to be pretty nasty. Okay, so I will just wanted to skip over that. All right, so that's how this goes. Now, notice I should say a couple things. You can there's nothing special about x and y. You can replace x and y with x and z, or y and z, or you can use x1 and x2. It doesn't matter what variables you use. Okay. Also, we can actually generalize this to other quadratic forms. Your book talks about this, that a quadratic form is really just they call it a homogeneous polynomial of degree 2, meaning you can have as many variables as you want, as long as each term are terms like this, where you just have either a variable squared or a variable times another variable. Okay, and that's just called a quadratic form. And all of those can be actually written, it will have a corresponding matrix for it. Now, I just wanted to give you one more case of this, and that is a ternary quadratic form. So a ternary quadratic form is a polynomial in 3 variables like this, where we have an x squared, y squared, z squared term, as well as an xy, xz, and yz term. There is no xyz term. Right? There is no xyz term, and there's no x term, no y term, z term. So we're just focusing on the terms of degree 2 here. And not surprisingly, you can see that this can be written as this product of here in the MF. In this case, we have a d over 2, e over 2, d over 2, b, f over 2, e over 2, f over 2, and c. So you can multiply this out, but if capital F is this polynomial, then this can be written as a product of this row vector xyz times mf times this column vector xyz. And once again, we can see that this is symmetric and real. So it's orthogonally diagonalizable. So once again, we can write, we can find an orthogonal matrix Q and a diagonal matrix D. Only in this case, these are 3 by 3 matrices, such that QT MF times Q is equal to D. Okay, and once again we can make a change of variables. In this case, x prime, y prime, z prime will be Q times x, y, z. And I think this is going to be, I think this should be Q transpose. If I did this right. Yeah, this should be Q transpose. Okay. Sometimes it didn't affect in the last example because Q was symmetric, but anyway. But after this change of substitution and this change of variables, we can get that this f of x prime, y prime, z prime is in particular it's lambda 1 x squared plus lambda 2 y squared plus lambda 3 z squared. And again, I think this should be, the prime should be over here. Okay. All right, so I changed the 4 to a 6 just so it's a little more interesting here. And then we can see that in this case there's no xz term or yz term. So mf in this case is going to be 1, 1, 3, corresponding to the x squared, y squared, and z squared terms. And then the xy term is negative 6 divided by 2. That's negative 3. So we get negative 3 here and here, and then zeros everywhere else. Okay. All right, and then we can take the determinant of this matrix, or the determinant of this matrix minus lambda, to find the characteristic polynomial. Okay, and fortunately, because all the zeros here makes the computation very nice, you can expand along this row. We get 0 minus 0 plus 3 minus lambda times the determinant of 1 minus lambda minus 3 minus 3, 1 minus lambda, which is 3 minus lambda times 1 minus lambda squared minus 9. Okay. All right, and you can play around with this, but you can see that obviously if you set this equal to 0, you get lambda equals 3 as an eigenvalue. But you also get that lambda equals 4 is also an eigenvalue, because 1 minus 4 is negative 3. And then you can also get lambda equals negative 2 is also going to be an eigenvalue, because that's basically you can multiply this out. I was being lazy, but you can multiply this out, and this becomes lambda squared minus 2 lambda minus 8, I think. So you can proceed. But the bottom line is these are the eigenvalues, and negative 2 is the smallest one. So we can see that negative 2 is bounds. Well, we can do a substitution. So we're looking at negative 2 x squared, or x prime squared, plus 3 y prime squared plus 4 z prime squared. This is equal to x squared plus y squared plus 3z squared minus 6xy. Okay. And we can see, because we have a negative eigenvalue as well as a positive eigenvalue, we can see this is indefinite. And we can also see that this will be bounded when x squared plus y squared plus z squared equals 1. Then this is bounded by negative 2 and positive 4. Okay. Okay, and again, to find where you get equality here, you just have to find the eigenvalues of this matrix, which are not hard to find. But I'll let you do that on your own. Okay, so that's all I have. So, but the main thing you want to be able to do is find the corresponding matrix for a quadratic form, find the characteristic polynomial, find the eigenvalues, and then do a change of variables. Find the change of variables that makes it, basically replace your original form with a slightly nicer quadratic form, which is easier to analyze. So that's all for today.